Welcome to Decode Tech. Have you ever wondered, how does my computer actually work? Or what's actually happening inside my phone when I send that text message? Well, that's what we're going to discover a little bit today, how your computing devices actually work under the hood. And hopefully till we're done, you'll understand it just a little bit better and can understand a little bit more about how your computer actually works. So to better understand this, let's look at a problem, counting everyone in a room. There's a couple different ways you could do this. You could use tally marks on a chalkboard, or maybe count on your hand. If I were to ask you off the top of your head, how high can I count on one hand? You'd probably say 5, which is what I would have said. 1, 2, 3, 4, and 5. But I would like to suggest I can count much higher, actually 32 on one hand, if I use patterns instead of the presence of a finger being up or down as a value. And so instead it would look something like this. 1, this would be 2, this would be 3, and disregarding its normal use, this will be 4 in our case, this will be 5, this will be 6, and this will be 7. And I know that doesn't make sense right now, but give me just a little bit and I'll explain. So how does this relate to computers? Well, computers are kind of simplistic, kind of like my hand was. And the resource computers have is electricity, either from the wall or from a battery, like in your laptop or cell phone. And this electricity maps well to your fingers being either up as electricity flowing, or your finger being down as electricity not flowing. And you may have heard that computers speak a language called binary, which the name bi means 2, so binary only has 2 symbols, either a 1 or a 0. And as long as you have enough bits or fingers like I had, and a bit just being something that can store a binary 1 or 0, you could represent theoretically any amount of data as long as you have enough bits, or 1s and 0s. So to better understand binary, let's first look at the numbering system we're most familiar with, the decimal system. So here we have 123, obviously. And how do we know that? Well, we know there's a ones place, a tens place, and a hundreds place. And so what we're actually doing is 1 times 100, 2 times 10, and 1 times 3, which gives us 100 plus 20 plus 3, and that equals 123. So we just do that instinctively. But if you look at a binary number, you should be able to tell this is probably 0 because there's just 3 zeros here. But binary system is different. And here we have a 1s, a 2s, a 4s, an 8s, a 16s, a 32s place, and so on, because binary is based on powers of 2 instead of base 10 like our decimal system is. If we would instead have a 1 in the far right placeholder, we would have 1, and then if we'd have a 0 in the 1, and the middle column, or the 2s, would be a 1, and there would be a 0 in the 1s, that would be 2. Or, like on my hand, when I had my thumb up, that was in the 1s place, so that was 1. And then when I put my thumb down and put my index finger up, that was 2. And when I kept my index finger up and put my thumb back up, that in turn gave me 3, because I had a 1 in the 1s place and a 1 in the 2s place, add them together, and we got 3. And I could have kept going up to 32 on one hand. So what if we have binary number 1 and we want to add 1 to it? And 1's the highest value in binary, so how does that look? Well, let's look at decimal to better understand it. So in decimal, 9 is the highest representation we have. So if we have 99 and we want to add 1, we roll the 9s over to 0 and add a 1 in the leftmost column to get 100. And in binary, it's very much the same way. If you have a 1 and you add 1, you change the 1 to 0 and put a 1 in the leftmost column. And we know that binary has a 1's place, a 2's place, and a 4's place. So now it has a 0 in the 1s and a 1 in the 2. So this is the binary representation for 2. But now how do we represent other information? Say we want to represent some text on the screen. Well, what if we would relate numbers to letters? Turns out years ago, humans came up with a standard for doing this. And it just so happens that the capital letter A stood for the decimal value 65. And there's a whole chart of 128 or 256 values that are mapped from bits to letters. So this might lead to you asking, how does a computer distinguish between a letter or a number then? Well, computers go by context, and so whether you're in your calculator app, it'll know to use numbers, or if you're in your texting app or Microsoft Word, it'll use letters. So if you were to receive a text message in your phone and it was given some decimal places, it would look in what's called the ASCII chart, or what humans came up with called American Standard Code for Information Interchange. And as I showed before, the capital letter A was mapped to 65, and then B is 66, capital C is 67, and so on. Back to this text message our phone received, if we were to receive the decimal values of 72 and 73, we would know by looking at the cheat sheet, for lack of a better term, the ASCII sheet that your phone looks off of, to see that, oh, I should be giving them the text message hi. And here I show hi exclamation point. If we instead added a third byte, or a byte is just another term for 8 bits, or 8 ones and zeros, because single bytes are not very useful for using to solve problems. People usually think of them in groups of 8, or 1 byte. So 8 bits equals 1 byte. So if we have 3 bytes, 72, 73, and 33 in decimal, and I show the binary down below, then we get the message, capital H, capital I, exclamation point. Now, what did we just do? This is called abstraction. In computer science, abstraction is when you take a low-level concept, literally low-level, down by the hardware, getting a general idea for how it works, and then abstracting away, realizing it's not very helpful to think of problems or solve problems in this way. So we abstracted away from the ones and zeros and the electricities from the wall up to letters. Now, we do run into a problem with ASCII because it is based off of 1 byte, which we know is 8 bits, and the highest value you can represent with 8 bits is 256. And you can probably guess that that is not enough mappings to map to all the symbols, especially adding in other languages that have apostrophes and all that. So there's a new standard they came up with called Unicode, and that helps us to come up with more symbols than just what we see on our keyboards here, and these things, which you've probably used before, called emojis. And because of this Unicode being based on 1, 2, 3, or even 4 bytes, they can represent thousands or millions of symbols and keep coming out with more and more of these emojis. And according to Apple, the crying face of joy is the most popular used emoji on Apple devices. And what is this emoji now? Well, your phone sees the decimal, 128,514, or if you look at the bits, you see the ones and zeros, very boring, but that is what your phone is actually using, and then mapping to the Unicode cheat sheet and displaying the crying face of joy on your phone or other device. But what actually is this emoji? Because now we see something different, some colors, some yellow in that emoji. Well, if we take the same bits, or I'm just going to abstract away the bits because we know they're electricity that are mapped to ones and zeros, then that are mapped to other data, and I'm just going to use the decimal 72, 73, and 33 that we had before with our capital H, capital I, exclamation point, or text message hi. And if we take them into a new standard that humans came up for representing color, called RGB, which stands for red, green, and blue. This is used very much like mixing paints in an art class, except for this is waves of light. So instead of storing just one dot on the screen, or pixel rather, they have a byte for each red, green, blue value to make up that individual pixel or dot on your screen. And so here, if we take the same bytes from our text message and throw them into something like Photoshop or some other photo editing program, it'll use red, green, blue, and it'll mix them together. And a byte, like we said before, is 8 bits, which the highest you can represent is 256. So we have 72 out of 256 possible reds and 73 out of 256 greens, and same with blues. Mix them together and we get this yellowish pixel. Now your computer is not storing that individual pixel per se, but instead the 3 bytes that make up that yellow color. And just for interest's sake, in a program like Photoshop or Lightroom or some photo editing program, you might see something like hashtag FFF00. That is a hexadecimal representation of the color, and hexadecimal is base 16 numbering system. The computers can't directly understand hexadecimal, but it's a little bit helpful for the humans compared to just a bunch of 1s and 0 binary digits. But getting back to our pixel, let's say we open this emoji in a photo editing program and zoomed way in, we would see what is called a pixelated image. And now you can start to see the individual pixels that make up an image. So an image is really just an abstraction for a collection of pixels. And you can see that the yellow pixel we made from those 3 bytes very much looks like a pixel that would be used in this image. So that's all for today's tutorial. I hope this was informative, and if you found it useful, please give it a thumbs up. And if you enjoy this content, why not subscribe? We're hoping to have more videos like this coming in the near future. This has been Decode Tech, and I'm your host, Denver. Until next time.